Welcome everyone, I'm Joachim Baumann, and in this video I'll be discussing our FACT 2022 paper titled Enforcing Group Fairness in Algorithmic Decision-Making, Utility Maximization under Sufficiency. This is joint work with Anikó, Hannák and Christoph Heitz. More and more decision-making systems rely on predictive models. These systems usually try to predict a decision-relevant attribute y, which is not known at the time of the decision. Therefore, a score function is learned to predict y, based on a feature space X. The output of this function is a probability P. A decision maker would then take a decision D based on this probability. There are many examples for such systems. For example, a bank that predicts applicants' repayment probabilities based on their credit history to take loan decisions. Or another example would be recidivism risk scores to help judges making bail decisions. However, there is a widespread recognition that those machine learning-based tools can go horribly wrong in practice. This can result in a number of problems, such as unfairness or injustice. One of the remedies the community has proposed is the enforcement of certain parity constraints. In this paper, we discuss how these constraints can be satisfied using post-processing techniques, which refers to the derivation of a decision rule to map a prediction to a decision. These so-called group fairness criteria are concerned with outcomes of algorithmic decision-making on individuals' lives. The goal is to avoid systematic disadvantages across socio-demographic groups. Many different group fairness criteria exist, the most popular of which are independence, separation, and sufficiency. However, several works have shown that these criteria are mathematically incompatible, and for this reason, we need to choose one group fairness criterion over others. Usually, prediction-based decision-making systems are not specifically optimized to ensure fairness. Instead, rational decision makers would rather optimize their utility, which is the sum of all individual utilities, ui. Here, we assume that the expected individual utilities only depend on the decisions D and on the probability P, and that both D and Y are binary, leading to this matrix with 4 possible outcomes. In this case, it can be easily shown that it is optimal to apply a single uniform threshold for all individuals. Post-processing algorithmic decision-making systems to satisfy a specific group fairness criteria can be formulated as a constraint optimization problem. So rational decision makers would maximize their total utility subject to some fairness constraint. This represents a selection problem where we must choose which individuals should be assigned a positive decision. Let us now have a look at optimal decision rules and how they look like if we enforce specific fairness constraints. Corbett-Davies et al. And Hart et al. Have shown that for independence, conditional statistical parity through positive rate parity and false positive rate parity, group-specific thresholds are optimal. Additionally, Hart et al. Showed that for separation, which is a combination of both through positive rate parity and false positive rate parity, optimal decision rules take the form of randomized group-specific thresholds. However, for the remaining 3 group fairness criteria, a similar result is still missing in the literature, and in our paper, we close this gap. PPV parity, or as it is sometimes also referred to, predictive parity, requires equal positive predictive values across the 2 groups, A equal to 0 and A equal to 1. Similarly, false omission rate parity requires equal false omission rates across groups. In contrast to equality of opportunity, we do not compare individuals with y equal to 1, but instead, we compare individuals who receive the same decision. Sufficiency then combines the 2 and requires both PPV parity and FOR parity. We now look at the effects of enforcing PPV parity, FOR parity, or sufficiency on utility maximizing decision makers. In our paper, we provide a formal proof for the corresponding constraint optimization problems. Here, we instead look at specific examples. Let us start with PPV parity, which is often also called predictive parity or the outcome test. Our approach consists of two different steps. First, we derive the optimal decision rules for a simplified constraint, where we assume that the PPV of both groups must be equal to a predefined value, which we call PPVT, and which must lie between 0 and 1. Second, we solve the full optimization problem by maximizing the decision maker's utility over discretization of all possible values of PPVT. As we will see, the solution differs depending on whether the number of individuals who are assigned a positive decision is predefined or not. For the first of these cases, where the number of selected individuals is predefined, the total utility is given. This means that any decision rule that leads to the given PPVT is optimal, as long as the selection capacity is exhausted. The group membership of the selected individuals does not matter, which represents a trade-off regarding the group fairness criteria statistical parity. Let us now look at the second case, where the number of selected individuals is not predefined. We find that in this case, any optimal fair decision rule takes the form of group-specific upper or lower bound thresholds. If the optimal PPVT is larger than a group space rate, a lower bound group threshold is optimal. However, if the PPVT is lower than the group space rate, instead an upper bound threshold is optimal. Notice here that the base rate is defined as the ratio of individuals belonging to the positive class, so y equal to 1, within a specific group. We use a synthetic dataset to visualize these different results. In particular, we look at 3 different populations, each of which consists of 2 groups, 0 and 1. We can see that in all 3 populations, the probability density function of group 1 is the same. The probability density function of group 0 is the same in populations 2 and 3. However, it differs in population 1. Each group consists of 20,000 individuals, except from group 1 in population 3, which only consists of 2,000 individuals. It is also important to mention that the decision maker's utility function is the same. In particular, without any fairness constraints, it would be optimal for the decision maker to apply a uniform threshold of T0, which is visualized with the red dashed line. Further notice that group 0 is disadvantaged, meaning that its base rate is lower in all 3 populations. The PPVs that result from a threshold T0 for all groups are visualized with a gray dashed line. The group fairness criterion PPV parity requires them to be equal for groups 0 and 1, but as we can see, this is not the case in any of the 3 populations. The PPVs differ by just a bit in population 1, but they differ largely in populations 2 and 3. Starting with population 1, if we enforce PPV parity, the optimal decision rules take the form of lower bound thresholds for both groups. These decision rules are visualized with the green solid lines T1 and T2, and all individuals with a probability that lies between T1 and T2 are assigned a positive decision T equal to 1. Compared to the unconstrained solution, group 0's threshold is decreased, while group 1's threshold is slightly increased. Unlike in population 1, in population 2, group 0's PPV is lower than the one of group 1 if fairness is not considered. Therefore, it is optimal to hold the disadvantaged group 0 to a higher standard in order to satisfy PPV parity. This result is likely to occur in practice because with a single threshold T0 that is optimal absent any fairness constraint, the disadvantaged group's resulting PPV is lower for groups with similar distributions. Let us now look at population 3. Due to the mere differences in the group sizes, all else equal to population 2, it is much more costly to change group 0's threshold relatively to group 1. Therefore, in this situation, it is optimal to deviate less from group 0's unconstrained optimum. The resulting optimal PPV, here visualized with a solid gray line, is lower than group 1's phase rate. And for this reason, it is optimal to apply an upper bound threshold for group 1. This means that a utility maximizing decision maker is willing to sacrifice the best individuals of the smaller group with a probability between T2 and 1. This result might be counterintuitive. However, it makes sense since the decision maker's total utility is measured, whereas we compare expected values to assess the fairness. In our synthetic data example, we see that in order to optimally satisfy certain group fairness criteria across groups, decision rules can lead to unfairness within the protected groups. We formalize this by introducing the notion of so-called within-group fairness with respect to protected attribute. A decision rule satisfies within-group fairness if there are no two individuals in the same group where the one with the higher probability is assigned a negative decision and the individual with the lower probability is given a positive decision. Applying an upper bound threshold therefore represents an extreme form of within-group unfairness. In our paper, we further showed that within-group fairness is always violated for all but one of the groups if the group fairness criterion sufficiency must be satisfied. Let's now complete the previously introduced table. We know that optimal decision rules satisfying PPV parity always take the form of group-specific lower or upper bound thresholds. And the same is true for false omission rate parity. Furthermore, in order to satisfy sufficiency, it is optimal to apply group-specific thresholds. In most cases, these thresholds must be randomized for all but one of the groups. The exact form of the optimal decision rules under any of these three criteria depends on the group's probability distributions, on their sizes, and on the decision maker's utility function. In our paper, we show this in more detail for the case of recidivism risk predictions using the COMPASS dataset. Existing work on group fairness for machine learning-based decision-making usually just considers group-specific thresholds. We show that for three group fairness criteria, this is not necessarily the case. Surprisingly, under PPV parity or FOR parity, it can be optimal for decision makers to apply an upper bound threshold for one group, leading to the omission of the most promising individuals. In the long-ranking scenario, for one of the groups, this would mean that individuals who are most likely to default are granted a loan, whereas those who are most likely to pay back their loan are in fact not granted money. Furthermore, our work shows that there is a trade-off between fairness across versus fairness within groups. Within group fairness is always violated for all but one of the groups when the group fairness criterion sufficiency must be satisfied. Thanks a lot.